4, 3, 2, 1, 0.
Hello everyone. Welcome back to a new video of Team Scientify. Hope you are doing well.
This is a continuation of our previous video, and here we will study about statistical regularity. First, we need to understand what it means. So, we take a random experiment E, where it will be repeated n times under identical conditions. And there is an event A of E which occurs NA times. So, the ratio NA by N is the frequency ratio of A and is denoted by FA. Now let's say this experiment E is repeated a very large number of times. Then we will see that the frequency ratio FA, which is NA by N, gradually stabilizes to more or less a constant. That means that FA tends to a constant number as N becomes larger and larger. So this tendency of FA to stabilize, which means that this tendency of stability of the frequency ratio is called statistical regularity. Now we will define probability. Let the event space S of a given random experiment E be finite. Then the probability of A, which is an event, and here A is a subset of S, can be defined as PA equal to M by N, where N equals to the number of distinct elements of S and M is the number of distinct elements of A. Now there are 4 deductions from this. The first one is 0 is less or equal to PA less or equal to 1. For this, we have PA equals to M by N. And here 0 is less or equal to M is less or equal to n. Or we may write 0 is less or equal to m by n is less or equal to 1. So from here 0 is less or equal to p of a is less or equal to is less or equal to 1. So this is proved. The second deduction is PS equals to 1. For this we may write PS equals to n by n. As S is the even space, so it contains all the distinct elements. So this gives us 1. Hence proved. The third deduction is P of O equals to 0. Now for this one we may take 0 by n. So this gives us 0, which is proved. And fourthly, this equals to 1 minus PA, which means all the elements of the event space except the elements of A, the event A. So n minus m by n, this gives us 1 minus m by n, which is equal to 1 minus PA. So this is also proved. Now we have a theorem of total probability. If A1, A2 till AK are pairwise mutually exclusive events, then P of A1 plus A2 till AK would be equal to the sum of the individual probabilities, which is P of A1 plus P of A2 plus till plus P of AK. So how do we prove this? For this we take n to be the total number of simple events of the corresponding random experiment E, of which Mi are favorable to Ai, where I is equal to 1 to till k. Now since the events A1, A2 till AK are mutually exclusive, the total number of simple events favorable to the event A1 plus A2 till AK is M1 plus M2 till MK. 0 is less or equal to Mi is less or equal to Ni is less or equal to n. Here I is equal to 1 till k. Then by the definition that we have learned, P of A1 plus A2 till ak would be equal to m1 plus m2 plus this goes on till mk by n. Now we can separate this, so m1 by n plus m2 by n, this continues till mk by n. This gives us p of a1 plus p of a2 till the last term p of ak. Hence, the theorem is proved. This brings us to conditional probability. We are going to take E to be a given random experiment and A and B are two events of E where probability of B is not equals to 0. So the conditional probability of the event A on the hypothesis that the event B has happened can be denoted by this, and this is defined by limit capital N tends to infinity n AB by NB, assuming that this limit exists. And NAB and NB are the number of occurrences of the events AB and B respectively. Please stay tuned for more videos on our channel.
This is all about today's topic. Thanks for watching. Hope you like the video.